All right, we're back. So, sorry, I'm apparently not playing with a full deck today. All right, this is the definition of the matrix of the abstract linear transformation with respect to, pair of abstract bases, beta for the domain, gamma for the codomain. You take the values of the transformation at the domain basis and calculate the coordinates with respect to the codomain basis. You slather those things together, that defines the matrix. Now, I was trying to derive that concept from the natural calculation, and I just got, stumped somehow here. And let's see here if I can kind of recover this. I don't think this was helpful. I was, but all right. So with this in mind, I wasn't able to make the. So if you look at this, right? If I call this matrix A for the sake of discussion, right? What is Aij equal to? If I look at the, so I'm in the jth column, we're looking at what? T of Vj, right? The gamma coordinate of that. Right? Then what? Well, that's a column vector. What I have written right, which is not right yet. There's no I yet, right? So then what is the row? And then you're picking the ith row, right? So you just say, okay, the ith component of that, right? So look over here. What do I have? I've got exactly that, but what's the deal? The I and the j, flippity-flopped. So sum over I 1 to n, sum over j equals 1 to m of a j I x I e j. Hooray! Now, this is exactly the matrix product of the t beta gamma with the matrix of x in the beta coordinate system. That's what that is. Of course, if I had my head screwed on straight today, we should have been anticipating this, because it's basically the same thing we started today with the standard matrix. It's just now we're dealing with the abstract basis, right? Which means things get more cluttered because we have to look at the basis. We have to use both bases to fully understand this. Does this make sense? Did you guys calculate any of these in your course?
No.
Okay. So you should certainly see an example of this then, right? I think everything I have on this board over here, we will remember. Actually, I'm about to do an example, so I can just erase it, right? All right. So I just gave you that's the definition of the, and it also is consistent with the definition of the standard matrix in the regular case. It's just in that case we don't put the beta gamma because it's understood, oh, you're working with the standard basis, you don't need to denote it, it's just the default.
Okay.
So, and likewise, you don't even need the of gamma things over there, because if you're just calculating the value of t of e1, what's the coordinate vector of t e1 with respect to the standard basis? Well, it's t of e1.
Okay.
Anyway, things get simpler with that case. Now here's an example. I guess this is example 2 because I did that other column 2 example earlier. I didn't number it, but I should have. How about this? We could look at T, a mapping from, I don't know, let's say second order polynomials over the reals to, I'll keep it relatively simple, first order polynomials over the reals. All right, and we'll think of P2 as being the span of 1x, x squared, and this one will be the span of 1 and x. Right, we're going to use 1x, x squared as the basis for P2. We're going to use 1 and x for the basis of P1. All right? And so we're going from a 3-dimensional space to a 2-dimensional space. And we'll let T f of x equal to f prime of x plus f of x. Just to pick an example, all right? Let's find, so let me name names here. Name names. Did I ever tell you what I think about not naming names with pastors? So pastors think that not naming names is important because they don't want to slander people. Something like that, right? Maintain the unity of the brethren. But the thing is, by not naming names, you leave the impression that you're talking about a whole plethora of people. So actually not naming names is implicitly slanderous because of the way people think. Because they always think, who's he talking about? So if you're going to make a comment about Joel Osteen, talk about Joel Osteen, right? I mean, name the person you're criticizing. Be open, be direct. It's important, and it's missing in our leadership often. Because once you name a name, you have to be precise about your criticism. You can't just vaguely shadow box against people who may or may not exist. So anyway. So this is the beta basis, this is the gamma basis, and I would suggest that we write f of x equal to, I usually use ABC for this kind of thing, like a plus, I usually use about ax squared plus bx plus c. That's what I would typically write, right? And then I draw a picture. All right, here's the picture I draw. So here's my v over here, w. T maps from here to here. Then we've got phi beta. We've got phi gamma over here. Down here, we've got, R3. And over here, we've got R2. All right? And here, we can look at the mapping, the left multiplication by the matrix of T with respect to beta gamma. That's the sum total of what's going on here. And so this is the other way I like to characterize the standard matrix, which is that left multiplication by T beta gamma is equal to this mapping, right? And that mapping, the first shall be last, right? So phi gamma comes last, so we go phi gamma composed with T composed with phi beta inverse. So phi beta inverse, it takes something down here, maps it to here, T takes that over to there, and gamma takes you back down here. But this is, let's see here, another way I could write, but oftentimes it's more convenient to look at it this way. Like really what's going on is that the matrix, like we were just writing over there, the matrix of T of, like T of f of x, right? With respect to the gamma basis should be equal to the matrix of T beta gamma times the coordinate vector of f of x with respect to the beta basis, right? That actually is oftentimes how I calculate the matrix. Let me finish this thought, okay? So, all right, so here, what is T? So this is my, my f of x is here, right? Equal to ax squared plus bx plus c, right? So what's the coordinate vector of f of x down here? We can do that much before we do anything else.
The coordinate vector here.
Yeah, what's the coordinate vector of this?
ABC.
Nope. You fell for my trap. Close though. One of your coordinates was right. Remember, coordinates, basis is ordered. So if I do 1x squared, I've set us up to, it's, yeah, CBA. All right. What's T of f of x? I'll do that over here. Like, what's T of f of x? And I'm again using this formula here. So f prime is what? 2ax plus b, right? And then f of x is plus ax squared plus bx plus c, right? So if I clean that up a bit, we've got, let's see here, b plus c plus parentheses 2a plus bx plus ax squared, right? That would be a better way to write the formula because it respects my choice of basis. And oh, oopsie, yeah, this won't do, will it? So is this problem well defined? This got to go because that is not in P1. So let's you go. You know what? Let's put, instead of putting f there, let's put f prime prime of x there. Now that's more exciting. Okay. All right. So f prime prime of x just gives you what? Plus 2a, right? All right. So we've got b plus 2a plus 2ax. So there's our tf of x is here, right? Equals to that. What is the coordinate vector of t of f of x with respect to the gamma basis?
Where are we?
Right here.
The coordinate vector of f of x.
So in other words, what's the coordinate vector of this with respect to gamma basis? That I know. This one, I put the right, it's b plus 2a, right? And 2a, there you go. I mean, that's that. All right, so check this out. All right, what we got is we want this to be, what was it? Right, like b plus 2a, right? And then 2a down here, right? That is supposed to be equal to this matrix, which we don't know yet. How big is the matrix, though? It's going from 3 dimensions to 2 dimensions. So we're looking for a 2 by 3. 2 by 3. And what matrix, what are we feeding into it? Well, C, B, A. So whatever we put there is, by definition, the standard matrix, not the standard matrix, the matrix of this linear transformation with respect to this pair of bases. Yeah, so like if I wanted to simplify a linear algebra course, this is like the first topic I dump, because this is like the hardest thing in it. Not this per se, like I always get students to get good on this, but like fully understanding how to change coordinates and how to use that to do things, like that's probably the harder side of linear algebra, really. Like so much of linear algebra is really kind of easy, right? I think it is anyway, but what do you put here though? You see it? You just look at it, you go, oh, well, I know there's no C, so 0 for my C. I need 1 B, I need 2 A's, you know, and then down here I just need 2 A's, so I go 0, 0, 2, and there you go. Now, of course, this you could also look at as the matrix formed by like the coordinate vector of t of 1 with respect to the gamma basis, and then the coordinate vector of t of x with respect to the gamma basis, and then the coordinate vector of t of x squared with respect to the gamma basis. And because t of 1 would have been what? 0, right? What would be t of x? We differentiate once, add it to the second derivative 0, first derivative 1, you got a 1 here. Double derivative, when you feed it to the formula for t, you just get 2, right? Oh, my bad, I'm missing something here. It was f prime plus f prime prime, right? So we get what? 2x plus 1. 2x plus 2? Right? 2x plus 2, yeah, my bad. I can't calculate my own formula. So do you have to do this pictorial way of doing it? I find the pictorial way is, like, I can get almost probably 80% of the people who take linear algebra to understand the pictorial way after I do about 4 or 5 of them. But you can also fall back on this method, which is kind of more like our definition of the standard basis. I use both in my thinking about what the matrix of a transformation is with respect to bases. And then, of course, what is, well, the coordinate vector of 0, 0. The coordinate vector of 1 is just 1, 0 because that was the first thing in the basis. And the coordinate vector of 2 plus 2x is 2, 2 because that's our gamma basis. Make sense?
Yep.
Cool. The thing is, once you can do this for a pair of abstract bases, you can do it for any pair of abstract bases, right? So now you can do the hideous thing and ask the question, but doesn't that mean the matrix is not uniquely defined? What if you chose a different pair of bases? What would happen then? How would that be? And the answer is, it would be different. It would be different. And then the question is, how different would it be? Well, let's see. All right. And so I'll draw the picture. And the picture, if you follow it, allows you to derive the formula. So, wowzers. So here's my V. And here's my W. Down here, I'm going to draw, this time, 2 copies of Fn and 2 copies of Fm, because I want to talk about what happens if you choose 2 different coordinate systems. How do they relate? How does the matrix of a given linear transformation relate when you compare it? Different choice of basis. So let's see here. So we have we've got our mapping up here, T, and I'm going to suppose that we have 2 different bases. We've got like basis beta and we've got basis beta bar, we've got basis gamma, we've also got basis gamma bar. Okay? And so we've got, for example, phi beta, we've got phi beta bar, we've got phi gamma, we've got phi gamma bar. So down here, to get, you know what, let me put the bar first over here and then unbar second for the sake of making my picture less cluttered, okay? So with this choice of diagram, I can picture this as left multiplication by the matrix with respect to beta gamma. That one would be that one. And the formula for that is what? Like left multiplication by T beta gamma is equal to like phi gamma composed with T composed with phi beta inverse, all right? So you gotta watch me. You go from here, phi beta inverse up to here, T over to there, gamma back down. That's this formula. But if you can do that, you can just as well do it with the barred coordinate system, right? You can do it down here, like so, right? You can talk about L of T, matrix of T with respect to the barred coordinate systems, beta bar, gamma bar, and that's going to be phi gamma composed with T composed with phi beta inverse, but of course with bars here, okay? Okay, so then my question is just this, right? How is T beta gamma and T beta bar gamma bar related? So what do you think we should do? How should we figure out how those are related? How can we derive it? See, I want to make sure students who take my linear algebra don't have to look up in a book how coordinate change works. I want them to understand how they can derive it for themselves if they need to, in whatever formalism they're working in. Because a lot of books tend to bury this in, like, they make a notation up a P and a Q, and they kind of have their own system of notation, and they kind of slog through it like that and give you formulas you can use. And I just think that's the wrong way of thinking about it. So here, what's the common thing? They're both describing T, right? So what I do is I just solve both of these equations for T. See, T is equal to, well, on the one hand, it's equal to, so I compose or precompose with, I hit it with phi gamma inverse on this side, right? Phi gamma inverse on this side, and then of course composed with L of the T beta gamma. And then I hit it with phi beta on the other side, right? Just like that. Listen, and that is diagrammatically totally unsurprising, because that's just the fact that you can start here and you can go, what can you do? You can go phi beta across here and then phi gamma back up, or you could just do T. It's two different ways to get from point A to point B. All right? But if you can do this for the unbarred coordinate system by symmetry of argument, of course the same is true for the barred coordinate system, right? So you got phi bar inverse composed with the left multiplication T beta bar gamma bar composed with phi beta bar, right? And what does this show us? Well, now all of a sudden we've got an equation that doesn't really involve T directly, let's say, but So now what do we do? Well, at this point, what I would do, the question is, what do you want a formula for? Do you want a formula for this equals to stuff with that? Or do you want that is stuff with this? I think I want a formula for this in terms of that, okay? So I'm going to try to isolate this. And the way I would do that is simply to, let's see here, like I'm going to compose with the inverse of this and the inverse of that on both sides, right? So like I'll compose with phi, what's the inverse of phi gamma bar inverse? Well, it's just phi gamma bar, right? So I do phi gamma bar composed with phi gamma inverse, composed with L of T beta gamma, composed with phi beta, composed with, well, phi beta bar inverse. All of that is equal to left multiplication by T beta bar gamma bar. Now we're going to have to fall back to a theorem we proved earlier today about the composition of linear maps on column vectors. All right? How's that go? Well, behold what we have here, right? This right here, what's going on there? That goes phi beta inverse. So phi beta inverse does what? It starts here, right? Phi beta inverse composed of phi beta. Right? So it's actually a mapping from Fn to Fn. See that? This right here is phi beta composed with phi beta bar inverse composed with phi beta, I believe. Did I do it wrong? I gotta be careful. I get flip-flopped. So phi beta composed with phi beta bar inverse is this mapping from here. But the point is, that is a mapping of column vectors, right? It's a mapping of column vectors. Likewise, this is, from F. This is actually from Fm to Fm. This is from Fn to Fn. All right? And this is what? This is from Fn to Fm. So, my point to you is this is the composition of linear maps. So what we can see from this is that this implies that the matrix of phi gamma bar composed with phi gamma inverse times the T beta gamma matrix times the matrix of this thing here. And so these things I'm writing, the matrix of phi beta composed with phi beta inverse, these things right here, these are the coordinate change matrices that your textbook, if you had one, would probably be calling like P or Q or some such dumb thing. And there you go, that's the formula that relates. Now let me be like the textbook and just call this thing P for a second. So you got P T beta gamma Q equals to, let's say, T beta bar gamma bar. So what does this mean? Like what's the relation of these two matrices? All right, so here's a special case. Special case. V equals to W and beta equals to gamma. And beta bar equals to gamma bar. Okay, so what I'm saying is, suppose you have a linear transformation from a vector space to itself, and you're looking at one choice of basis and then the same choice of basis over there, all right? In that case, you've got beta bar beta, and you've got beta beta bar. So if this is P, that forces this to be P inverse, because these are inverse maps of one another in that context. Generally speaking, they don't have to be inverses of another, because this can be a 4 by 4 matrix, this can be a 3 by 3 matrix. There's no, all right? So in this case, you get the formula P T beta gamma P inverse equals to T beta bar gamma bar, right? Now if that's the case, that's really special. That would make the matrix for the transformation and the coordinate changed matrix what are called similar matrices, right? They'd be similar matrices. In the relation P, T, Q equal to T like that, that's not a similarity transformation. That's something else. All right. So now both P and Q are invertible. So it's not nothing. But these are just kind of like two big discussions to be had in linear algebra, right? Like, okay, so you've got two vector spaces, V and W. You're looking at a transformation between them. All right, so then the question is, if I take that transformation, right, and I compare it to another transformation, you know, it's got a different formula. I can ask the question, hey, is that actually the same transformation, just with respect to like a different choice of coordinates or something? You know, like if I have a linear transformation, I have another, are they really the same transformation just with a different choice of coordinates? So if you're allowing yourself the freedom to change coordinates, both in the domain and in the codomain independently, then you can turn the screws and adjust P. You can turn the screws and adjust Q independently. That's far more freedom than the boxed case at the bottom, where you're assuming the same dimension for both, and, you know. So in the top case, it turns out like there's sufficient freedom choosing P and Q that you can always sort of reduce the matrix. You can choose a system of coordinates that reduces the formula for the matrix to the identity matrix padded with zeros. The size of the identity matrix is the rank of the rank of the transformation. Basically, what you do is you take your vector space and you form a basis which has the kernel of the transformation as part of the basis, and the rest of it you extend past that. The part that extends past that maps non-trivially to the codomain. Then you arrange the basis for the codomain such that when you look at the matrix of the transformation, you get the identity matrix with zeros around it. And the size of the identity matrix is not up for grabs, because the size of the identity matrix is pinned uniquely to the dimension of the kernel of the map, which is called the nullity of the map. Nullity of the map is is independent of your choice of basis. All right, it's geometric. So that's kind of boring in some sense. So what I'm saying to you is that's really a profound and annoying statement. But any two linear transformations from R5 to R10, if those two transformations both have rank 3, then they're the same linear transformation in the sense that I could choose a system of coordinates which would make them have the same formula. Now, some people would probably disagree with my characterization because I'm allowing for arbitrary choices of coordinates. Now, if you bring other ideas to bear, like you have to have orthogonal systems of coordinates, then what I'm saying breaks down. So I'm allowing general coordinate transformations in the linear sense in this comment. That P and Q are just invertible matrices. If you force P and Q to be orthogonal matrices, that's more structure. You can't necessarily get back to the identity matrix padded with zeros. But if P and Q can be anything invertible, you can you can select bases to make those, you can force the new T to just be the identity matrix padded with zeros. Okay. On the other hand, if you're working with a linear transformation from a vector space to itself, and you're using the basis in the domain and the basis in the codomain have to be the same one, and you're also insisting that you can't change them differently in the domain, and you're insisting you have to change the domain and the codomain basis at the same. You're really thinking of the domain and the codomain as being the same space, and you're looking at a transformation from the same space back into itself, really, conceptually. Well, then you're faced with a similarity transformation, and the question of whether or not two linear transformations are the same, endomorphism, that is linear transformation of vector space to itself, well, then that becomes the question of, if you look at if you look at two given transformations, and you look at their matrix with respect to a given basis, then the question is, are those two matrices similar? If they're similar, what that means is you can make a change of coordinates in the vector space so that the formula for the one transformation becomes the formula for the other transformation, right? Now that's most especially interesting if we start thinking about the problem of like diagonalisation. Like this is probably the place you saw it before. If we have a linear transformation and we've got some ugly formula, the question is, can we find a formula where the formula is like the first coordinate informs what the first coordinate goes to, the second coordinate informs what the second coordinate goes to, the third coordinate informs what the third coordinate goes to, right? There's no intermixing in the formulas. It's just like, T of x, y, z is x, comma, 2y, comma, 3z. This would be an example of a diagonalized transformation. It's a really simple formula. The matrix is diagonal. So that's an interesting question, like when are two matrices, when can you diagonalize a matrix? And so to answer that question, we have to study the theory of eigenvalues and eigenvectors. That's what that whole discussion is actually intended to do, is to answer that question. But I'll try to actually show you what I was talking about at the end of class next time. We should spend another lecture at least on coordinate change of linear transfer. This is a hard topic, and if you didn't see it in your course, then I should spend more time on it. So, sound good?
Yeah.
So hope. Oh, yeah, that's fine. And I think there's more in my notes. But yeah, cool. And then